Hey everyone, this is a video about the unit circle. We've done a couple of activities in class, so this is going to review that. So we began in class with a blank unit circle. A unit circle is a circle which has a radius of 1, so a radius starts in the middle and goes to the outside. And although they're not drawn past the circle, we're actually looking at a Cartesian plane. So think back to when you first learned about graphing, say in year 9, you had your x-axis and your y. Okay, so you had positive x, positive y, negative y. So that's the type of plane that we're looking at. So, there's that. So we've got some coordinates on here to begin with. So over here, x would be 1, y would be 0. Because we've got 1 across on the x, 0, 1, negative 1, 0, and 0, negative 1. I'm going to leave the coordinates for now and have a look at the degrees going around the unit circle. So over here we have two lots because we start at 0 and we end at 360. We're moving anti-clockwise, moving this way. So 0, 90, 180, 270. The first degrees we're going to look at are these 45 degrees, so we're cutting it in half. You can think of things like halfway between 90 and 180, but what we can do is go up by 45s. So we had one lot of 45, two which made 90, add on 45, we'll get 135, and you can keep going around till you've got all your your groups of your 45 degrees. Next, I can tell you that this first one is 30. Without knowing that's 30, you're sort of a bit stuck. But as soon as we know that one's 30, we can go up by 30s now. So this one's 30, 60, 90, 120, etc. So we keep going around. Now, obviously the unit circle covers really every degree there is, but when we're looking at our exact values, we're just going to work with these degrees here. Next, we're going to add radians to our unit circle. I've got a little diagram of here about a radian. It takes the radius of a circle, and a radian is taking that length and making it an arc around the circle. So that's 1 radian, shown by the red line. So what's interesting is you'll notice it fits 3 times in a little bit. It fits in pi times to a half circle. And does it keep going around? Yeah, it fits in 2 pi. So if we've got the unit circle and we know circumference is 2 pi times the radius is 1. So our circumference of our unit circle is 2 pi. So having a look now, we've got 0 at the start, and halfway around would be 1 pi, and full way around would be 2 pi. So radians is basically our way of expressing the angle using pi instead of a degree. So filling those in, up the top here, we've got half a pi. So we've got pi over here, half pi, quarter of a pi. And I think I filled in all the quarters. So how I got to this one, so basically starting at, where'd my mouse go? Starting at 0 here, we've got 1/4 pi. Up here we actually have 2 quarters, okay? But 2 quarters is the same as a half. So I'm going to go around and be like 1/4, 2 quarters, 3 quarters, 4 quarters, 5 quarters, 6 quarters, 7 quarters, 8 quarters. But those are all going to, some of them are going to simplify. So we end up with a half, we end up with 1 whole, we end up with 2 pi. Okay, so now I'm going to do 30 degrees, pi on 6. You can think of this because we had half a pi, or we had a full pi that was divided into 6 segments. So that, and we're going from here to here. So that's pi on 6, equivalent to 30 degrees. And again, what I'm going to do to figure out all these is go 1 pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, 5 pi on 6, 6 pi on 6, 7, 8, 9, 10, 11. So some of those are going to simplify. Okay? So for example, 2 pi on 6, 2 on 6 as a fraction is the same as a third. 9 pi on 6 is the same as 3 on 2, 1.5 pi's. But basically, some people ask, how do you know your unit circle off by heart? Well, as long as you know that the whole circle is 2 pi, half is a pi, quarter is pi on 2, you've got your sixth here and your third and your quarter, and then you can just move your way around and fill in everything you need to know. So it's not about memorizing this whole thing really ever. Okay, now we're going to look at the coordinates, which is probably the harder part of the unit circle. So first of all, we need to understand that when we are looking at a coordinate here, okay, this x, this y, we are talking about this distance being x and this vertical distance being y. And that's what we're doing in any normal coordinate. So when we plot something like 3, 4, we're going 3 across, 4 up. But what we're going to do to work those out is treat that as a triangle. So just going back here, one thing we notice about the 40 degrees, 45 degrees, is that it creates a isosceles triangle. Because if it's 45 degrees here and this is 90, this one has to be 45 to add up to 180. And when you have the two angles in the bottom are the same, the two sides are the same. So instead of having x and y to figure out, they're both the same. So let's call them both x. We could call them both y. It doesn't matter, but they're both the same value. And we know that the longer side of this triangle is 1. And that's because it's the radius of the unit circle. It goes from the middle to the edge. So we've got a right angled triangle with sides missing, so we can use Pythag. So we're not going to use the angles. So we've got x squared plus x squared equals 1 squared. 2x squared equals 1, because 1 squared is 1. Sorry, I'm losing my mouse. Divide both sides by 2. Find the square root of both sides. And square root of 1 is 1. Square root of 2 is root 2. Now this is the interesting part. If you look online at some unit circles, you will find that some not so nice ones have the coordinate listed as 1 on root 2. We don't want to leave a square root on the bottom of a fraction. So we always know we can multiply a fraction by the same thing as long as it's the same on the top and the bottom. So just like a half, if you times the top by 3 and the bottom by 3, you get 3 on 6. So it's the same as a half. So we can do that with square roots. And what that will do is, because we've got root 2 times root 2 on the bottom, that's like root 2 squared. The root and the square will cancel each other out. And so we end up with root 2 on 2. So it doesn't look much simpler, but it's just a preferred way. We don't want a square root on the bottom of the fraction. So now we know that x equals that, which means that y equals that as well. So if we move back to our unit circle, just focus up here for a second, you'll see that there's our coordinate for that spot on the 45 degrees. You'll notice that I filled it in here, here, and here with the same numbers. That's because if I was to draw that same triangle over here, if I was to find out this angle here, it would be 45. So from here all around, it's 135, but from 180 to 135, there's 45 in here. And so we're going to get the same situation, except we know that this is the negative x axis, so which means that the x coordinate is negative, but the y will still be positive. It's actually in line with the exact same spot on the y-axis here, both of them root 2 on 2. So down here we get both of them are negative, and over here the x is positive again and the y is negative. And I think I might have now this isn't going to make too much sense with sine and cos yet, but you can see here that we've got x and y, and they're always negative, positive, both negative, and positive, negative. So it sort of gets this, what I call butterfly wings effect in the center. Because if we put the angle here, you can see that we kind of go up and we can go down and we get the same numbers. I might skip that for now and come back to it later. Okay, let's have a look now at 30 degrees. So here's 30 degrees from here to here. And we have the x and the y. And again, we're going to make that into a triangle. So at first glance, you're probably thinking that y is going to be half of x because we've got, this is half of the angle here and it just looks like it. In terms of a proof for that though, what we can do is reflect that triangle. So we do the same triangle here and we end up with 60 degrees here, 60 here, and 30 plus 30 is 60. Now when all angles in a triangle equal 60, you get an equilateral triangle, which means all the sides are the same. we know that this one and this one are 1. So what we've proven is that this side over here is also 1. And if that side is 1, if we take away half the triangle, that means that that leftover part is a half. Not just half of something, we know that is a half because we are working with the unit of 1, so that is half. So we've worked out our y coordinate already. That's going to go there. Now we need to work out our x coordinate. And again, we're going to use the idea of Pythagoras, because this side squared plus this side squared equals 1 squared. Filling those in, 1 squared is a quarter. Take a quarter from both sides and then you do the square root, and we end up with root 3 on 2. So we can't work out the root of 3, so we just leave it as root 3, but we can work out the root of 4, and that's 2. So that is our x coordinate. And again, you'll see that I have filled in the equivalent over here, but it's negative for the x. Down here they're both negative, and over here the y is negative. Really important to know that I didn't put it here. So we're not some people sort of think that because from here to here is 30 that maybe we'd start here, go here. We're not doing it in that way. So here to here is 30. The equivalent triangle is over here. From here to here is 30. Because what we need it to do is line up with the x-axis. So, or the y-axis, let's look at half, has to line up with half over here. Okay, we have one last one to fill out, and that is these ones up here. I haven't drawn up a page for these because what I would like you to notice is if I was to draw a triangle here, it would be 60 degrees down here, 30 degrees here. We basically get a flipped version of the triangle we just did for 30 degrees. So all we need to do for the 60 degree coordinate is to do the opposite of all the 30 degree coordinates. So again, you can see lots of patterns to do with the unit circle. So rather than thinking, oh, I need to memorize this whole thing, you wouldn't probably want to do those sort of proofs again and again, but if you can memorize just these 3 here, you will be able to fill in all of this unit circle. How does this relate to trigonometry? So you might have seen on an earlier slide that I sort of skipped past those mentions of sine and cosine we haven't talked about yet. So let's say we're looking at just any old point on the unit circle. We don't know where it is, so we'll call it x and y. So this distance is x, this distance is y, this one is 1. If I was to try and figure out x using trigonometry, so SOHCAHTOA, x is the adjacent to theta. So it'd be cos theta is adjacent over hypotenuse, which would be x over 1. X divided by 1 is just x. So what we have found out that on the unit circle is that this distance for x is equivalent to cos of that angle. Or I guess you could think of it as cos of that angle is the name we have given to representing that x coordinate. Same for sine. Sine theta is the opposite over hypotenuse, which is equal to y over 1, which is y. So another way of drawing this diagram. Yes, there's cos and sine. Where's my thing? Oh, there it is. Okay, so each point can be thought of as cos theta and sine theta. Cos, sine. So how does this relate to what we've done previous years? So let's look at this triangle here. 30 degrees, got 6 as the hypotenuse, x is the opposite. So we're going to use sine to solve this equation. We end up with sine 30 equals x over 6. So let's have a look at sine 30. So if this was a triangle on the unit circle, sine 30 is the y coordinate is a half. So it tells us that for any triangle with 30 degrees, the opposite side will be half of the hypotenuse. So just looking at this, I know the answer is 3 for x. What we've done in the past is when x was on the top, we have multiplied 6 times sine 30, and that's 3. So what we've just done in basically year 9 and year 10 SOHCAHTOA is you haven't really known what the unit circle was, but what you've been doing is just multiplying or dividing to find out the missing part of a triangle that is just a larger version. So maybe it's 3 times larger than a unit triangle, a triangle with a hypotenuse of 1.